Hi viewers, welcome to my class on mechanics of materials. In this class, I'll start with a new topic, shear force and bending moment diagram. Shear force and bending moment diagram help to identify the locations on a beam where maximum shear force and bending moment is acting. And based on this, the designer will be able to strengthen the beam. Before starting with the shear force and bending moment diagram, I'll explain the basic requirements like type of beams, loads and supports in this class. To start with, what is a beam? It is a structural member mainly designed to take up transverse loads, whereas column is designed to take up axial compressive loads. Beams, on the other hand, will support transverse loads on its axis. It will support mainly transverse loads. So the forces will be acting perpendicular to the axis. Some small components may come along the axis. So mainly it will be subjected to transverse loads. Beams are commonly used in civil engineering and structural elements. Even automobile frames, machine parts and other mechanical and structural systems, small components can be considered as beams and analyzed based on the principles of beams. Now let us discuss the different types of supports. Beam is supported at different points. It may be at one end or either end, or it may be supported at different points. Now let us discuss the nature of supports. Mainly there are three different types of supports. Let us discuss these supports used in the construction of beams. So first one is roller support. So these are provided with the rollers at the base, and the roller base in this example shown is horizontal. Now this will not prevent the lateral movement, horizontal movement of the member. So I have shown that a part of the beam, it's a roller support. Base is provided with the rollers. So since rollers are not restricting the motion in the horizontal direction, so it can move in this direction, and it only prevents the movement in the downward direction. So in this support can only prevent the downward motion of the beam part. So if the loads are transmitted in the horizontal direction, it cannot resist that force because it is not restricted the movement in that direction. So axial loads or the loads acting in the horizontal direction cannot be taken up by this roller support. So whatever the load is acting on this beam, part of the beam, this roller support can resist only forces perpendicular to the base of the roller. So the reaction from the roller base will be perpendicular to the base of the roller. This is only one end support I have shown. The other end should be supported. The beam cannot stay like this. Since it's a roller support, it has to be supported by another support at the other end. When it is subjected to a push like this, this cannot take up that inclined force. It will only give a resistance in the vertical direction. So the property of the roller support is it resists forces only perpendicular to the base of the roller, irrespective of the load transmitted to it. So it can resist forces only perpendicular to the base of the roller. When the base is horizontal, the reaction will be vertical. If the base is inclined, the reaction from that inclined base will be perpendicular to that inclined face. So this is the direction of reaction in this case, irrespective of the loads transmitted. the reaction is going to be perpendicular, and it cannot pull downward, it only push, because it is not fixed here, rollers are not fixed here, so it can only push from, so it can only take up the downward force, it prevent the downward movement, or downward force will be resisting, or if it's pulled up it cannot resist, it cannot pull back. So this is the resistance offered by a roller support. It can only prevent forces in the downward direction, it cannot prevent the lateral movement, or it cannot prevent the rotation. Let us find out a hinge support. Hinge, this is a hinge joint, and it's here it's fixed. So this is the joint, so it resists the forces in any direction. Unlike a roller support, it can resist forces in any direction. If it is pushed in this direction, the hinge will exert an opposite force. If it's pushed downward, it will exert an upward force. If the force transmitted is inclined, it will resist in opposite to that direction. So it can resist forces in any direction, but this cannot prevent the rotation. It cannot stay in this horizontal position like this, it will rotate, and because of the weight of the beam it will rotate down. So it has to be supported by another support, okay, other side or other end or somewhere in the middle. So it's only one end I shown. So the reaction direction usually it will be inclined, but it can be vertical or it can be horizontal based on the force transmitted to this hinge support. Generally we can take inclined reaction and we can assume components of reaction there. So we may treat it as a single reaction like this RA with an inclination theta. Theta can be 90 degree, 30 degree, or theta can be 0. So this is unknown reaction. So there are two unknowns, RA and theta. In case of roller support it was only one unknown, the direction was known, but in this case the direction is also unknown, the magnitude is also unknown. So instead of treating it as a single unknown force and unknown inclination, you often resolve this force into components and treat it as x component and y component. So you may take it as RAX instead of RA. Removing this RA, you can resolve it to components RAX and RAY. Now RAX is RA cos theta and RAY is RA sin theta. So that is a components, but we take it as RAY and RAX, where RAX is usually RA cos theta and RAY is RA sin theta. So whenever you see a hinge support, you can take x component and y component for the reaction. But if you are sure the force transmitted is vertically downward or vertical, you can take only y component. If you know that force transmitted is horizontal, you can take the total reaction as horizontal. But if force transmitted is inclined, if the nature of loads on the beam is such that the force transmitted to this hinge is inclined, then you have to assume two components of reaction at the support. So hinge support will resist forces in any direction, but it cannot prevent the rotation. If it is rotated, it can freely rotate with respect to this hinge. So it is not preventing the rotation, it cannot resist moment. So if it is trying to rotate, it will not resist it. But if it is pushed in any direction, the hinge support will resist that and forces will be developed. Reaction forces will be developed at the hinge support. Now another kind of support is fixed support. Fixed support is firmly fixed at one end and beam can stay with one support alone. With this fixed support, without supporting at the other end, it can stay, and it can resist forces in any direction. If you are pushing it in this direction, it can resist. Pushed it downward, it will resist. Pushed it with a inclined force, it will resist. So it can resist forces in any direction. It has got all the characteristics of a hinge support. Apart from that, it can also resist moments. So it will resist moment. If it is try to rotate clockwise direction, it will exert a anti-clockwise resisting moment. If you try to rotate in the counterclockwise direction, it will exert a clockwise moment. So that way it will resist. So the characteristics of fixed support is it resists forces in any direction, and also it prevents the rotation. So the reaction from this, you can take it as inclined, and again you can resolve into two components, x component and y component you can take, and also you can assume a resisting moment. And the resisting moment sometimes may be zero, depends on the forces transmitted. If no load is acting, there will not be any moment or any reaction. Neglecting the weight of the beam, there will not be any reaction or any resisting moment. Usually when a beam stays, because of its self weight itself, it will be producing a clockwise rotation, and in that case there will be a resisting moment in the anti-clockwise direction, not in this direction, anti-clockwise direction, and there will be a vertical force preventing this downward force. Weight is acting downward, so the reaction will be purely vertical. So we discussed the three major types of supports. Let us discuss the different types of loads that can act on a beam. So different types of loads. We have point load. Point load is the load acting on a limited area. Any load to act upon, it requires some area, but point load, it's acting over a very small area on the beam. It is not spread, it is concentrated on some smaller area. It's you are applying force with your finger, okay, just pressing with the finger. That is similar to the point load. Whereas if you are pressing with your palm on any surface, that will provide a distributed force. The forces is acting over a larger area and it is spread. So that is the difference between point load and distributed force. So here I have shown 2 point loads acting on a beam. Point loads is represented like this. Next type of load is uniformly distributed load. So it is uniformly distributed over the surface. So with the intensity of load, intensity there. Point loads is represented Newton or kilonewton. That is force unit, kilonewton or Newton. Whereas in this case, intensity will be given kilonewton per meter. What is the load acting in 1 meter length? In 1 meter, 4 kilonewton. Suppose 4 meter is there, 4 into 4, 16 kilonewton. So the intensity will be given. So these kind of loads, you can say it's a weight of the beam itself is a uniformly distributed load. So usually we neglect the weight, but the weight itself is usually a distributed load. In the building structures, you would have seen a beam, and over the beam usually the part of the load of the roof will be acting. That is going to be a distributed load. On a bridge, concrete will be spread over it with a uniform thickness. That will constitute a uniformly distributed load. So the intensity of load generally will be given in kilonewton per meter. So this UDL may be represented like this, or it may be represented. It's both the same type of load. This is also representing UDL, and you can also represent like this. Suppose the load is acting over a 6 meter. This 4 kilonewton per meter is acting over 6 meter, and then you can replace this load by a point load for the purpose of obtaining the reactions at the supports. So you can replace it by a point load. That is only for the purpose of finding out the reaction, considering the equilibrium, to consider the stability of the beam. You can replace it by a point load, but to identify the shear force and bending moment, that is it will produce a different effect on the beam. point load and UDL will have different effects on the beam, but for obtaining the reactions at the supports, you can replace it by a point load. So how to replace it? What will be the resultant load? Because 4 kilonewton for every meter it's acting. So for 6 meter it will be 4 into 6 or 24 kilonewton. So you can replace this by a point load of 24 kilonewton at the center of this span 6 meter. Okay, 3 meter from here or 3 meter from here, or from this support it will be 2 plus 3 5 meter. So this is the replacement at the center. At the center you can replace this, remove this and put 4 into 6 or 24 at a distance of 6 by 2 or 3 meter. So from this support it is going to be 5 meter. So this is the replacement for this UDL. Another type of load is uniformly varying load. In this case the load will be varying from one intensity to another intensity. It can vary from 0 to a maximum intensity, or it can vary from one intensity to another intensity. Now these are the two types of UVL. It is uniformly varying. The intensity is uniformly varying. The intensity is not constant throughout. So it is maximum here, it is 0 here in this case, and the variation is linear or uniform. Okay, so it is not irregular. You can have a non-uniformly varying load, but in this case the load variation is uniform. So this kind of load, triangular load, this is a triangular load with 0 intensity at one side. So in this case, this side it is 7 kilonewton per meter is the intensity, here it is 0 intensity. So if it was full throughout the length 7 kilonewton per meter intensity, then the load will get as 7 into the span. Okay. Now in this case 50% of the load is removed. So 7 into span divided by 2, that will be the load. If it is UDL, UDL will be like this. So if it's UDL, load will be 7 into 6. But in this case, it is half of that. So 7 into 6 divided by 2. So that will be 21 kilonewton. So 21 kilonewton is the resultant load due to this UVL. Now when it is a UDL, you replace the load by at the center, but in this case major part of the load is concentrated here. So the load, resultant load will be nearer to this major intensity. So the resultant load will be somewhere nearer to this end. So what is the location? To calculate the load, you calculate the area of this triangle. So 7 into 6 divided by 2, that will give the area of the triangle. So the area of the triangle, it's a resultant load. And to find out the location of the load, you can find out the centroidal distance from the vertex. For a triangle, we know the centroid is from the vertex, it is going to be 2/3 of this span 6 meter, or from this side it is going to be 1/3 of 6. So that is the location of the resultant force, that through that point the resultant will act. Now resultant will be acting like this. This is the resultant load, 7 into 6 divided by 2 or 21 kilonewton. So you can replace this by 21 kilonewton. The location where you have to replace it can be calculated as this span into 2 by 3. From 0 intensity side it will be 2/3. From the other side it is going to be 1/3. 6 into 1 by 3, or this is going to be 2 meter, and from the 0 intensity side it is 4 meter. So this is how you replace a triangular load. In case of a load varying like this, you can split this into a UDL and a triangular load. UDL, you can calculate the intensity. UDL is going to be like this is 6 kilonewton per meter, and remaining will be 4 kilonewton per meter. So a UDL of 6 kilonewton per meter, you can calculate the resultant load and replace it at the center. Whereas a triangular load, you can calculate that load 4, this part will be 4 into that span divided by 2, and you can replace at a distance of 2/3 from that. So you can replace this as 2-point loads, one corresponding to UDL and another corresponding to triangular load. Okay. Another type of loading is couple acting on a beam. Strictly speaking, couple is two parallel forces acting in opposite direction. Couple is produced by two equal opposite parallel forces acting over usually a short distance. Since it is a two parallel equal forces, the resultant force is taken as 0. Resultant force in any direction, it's going to be 0, but it will produce rotating tendency when it is applied, and the magnitude of the couple you can take in the moment summation. So couple is represented by the magnitude like this, 20 kilonewton meter. That is the magnitude of the moment produced by that couple. So in the force summation, this couple should not be considered, but in the moment summation, you can directly add this value. If it's clockwise, you can take plus. This I have shown clockwise. If the couple is anti-clockwise, you can take minus sign based on the sign convention. Okay, so I am going to take clockwise as positive, anti-clockwise as negative. So in this case, it's a clockwise couple. In the moment summation, you can take plus 20 kilonewton meter, but in force summation, you should not consider this couple because it's two equal opposite parallel forces. One force is plus, the other force is minus of equal magnitude, then summation will be 0, but it will produce rotating tendency. Now let us discuss the different types of beams. First, let us discuss a simply supported beam. So beam supported by a hinged support at one end and roller support at the other end can be considered as a simply supported beam. Now, different types of loads may act on the beam. So it's supported by a hinged support at one end and a roller support at the other end. And hinge will prevent this lateral movement. Any lateral load, any inclined load acting on the beam, hinge will take over it because it can support forces in horizontal direction also. But roller cannot take up this load, so both roller support is not possible because it cannot prevent the horizontal loads, cannot take up the loads acting inclined on the beam. So either side roller support is not going to be stable beam. So usually common is like one end hinge support, other end roller support. Roller support will allow the expansion of the beam if it prevents the development of thermal stresses on the beam. When the temperature rises, the beam material may expand, and this roller support will provide the provision for expansion of the beam. Hinge support cannot allow the movement, but roller support can allow small movement in the lateral direction. So it helps in preventing the thermal stresses induced on the beam. Another kind of beam is overhanging beam, and beam extends beyond the support. Okay, it's extending beyond the support. Either one side or both sides can be considered as an overhanging beam. So it's overhanging and this is also overhanging. So either one side or both the sides it should extend. Cantilever beam is a beam fixed at one end and free at the other end. And another type of beam is continuous beam. It has got supports more than at 2 points. So if a beam is supported more than at 2 points, it can be considered as a continuous beam. So it's supported more than at 2 points. So this is a continuous beam. And another type is fixed beam. Both ends you have fixed supports, and loads are acting on the beam. So these are the different types of beams. Out of the beams discussed, some are statically determinate, like first three kinds of beams which we discussed: simply supported beam, overhanging beam, and cantilever beam. They are statically determinate beams. So that means you can solve these unknown reactions at the supports using the equations of equilibrium alone. Using the equations of equilibrium, that is sigma fx is equal to 0, sigma fy is equal to 0, and sigma m 0, you can solve the unknown reactions. But in case of continuous beam and fixed beam, you cannot find out the unknown reactions using equations of equilibrium alone. We require compatibility equations to solve these kind of beams. So they are known as statically indeterminate structures. Statically indeterminate structures. So in our discussion, we will be discussing only the statically determinate beams. Okay, that is simply supported or hanging and cantilever beams. And that's all for today. Thank you for watching.